All right, the spinner. The spinner below shows 10 equally sized slices. Kyoko spun the dial 50 times and got the following results: 23 white, 18 gray, 9 black. Fill in the table below. Round the answers to the nearest thousandth. All right, so here we go. From Kyoko's results, compute the experimental probability of landing on black. Okay, so experimental probability, I would go from her 50 rolls. I'm just going to look at those 50 rolls. And 9 of those are landing on black. 9 out of the 50. All right, so I would say the probability, the experimental probability would be, get a pencil here, would be 9 out of 50. All right, if I type that in as a decimal, 9 divided by 50 is going to leave me with an 18% chance of that happening experimentally. Now, assuming that the spinner is fair, compute the theoretical probability. Okay, so let's just say they didn't do any of this, and I just look at this picture, and I want to know what's the probability of landing on black. Well, there are, how many spaces are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 spaces. 2 of them are black. So the probability of landing on the black is 2 out of 10, which is 20%. So these things, experimental and theoretical, aren't the same here. This next question, assuming that the spinner is fair, choose the statement below that is true. Now let's read through here. As the number of spins increases, we expect the experimental and theoretical probabilities to become closer, though they might not be equal. That sounds very, very likely to happen. But let's just check these other ones just to see. The experimental and theoretical probabilities must always be equal. Bang, not going to happen. As the number of spins increases, we expect the experimental and theoretical probabilities to become further apart. Bang, not going to happen. This is what's going to happen. The more times they were to spin that thing, we would expect these numbers to get closer and closer. You know, they're not too far off now, but if we'd have done 100 spins, we would have expected them to get even closer. 1,000 spins, even closer. They might not be exactly. This isn't going to change, okay? But this number is going to get closer and closer to the theoretical probability the more times you spin that thing. All right. Go finish up those problems. We are getting super close. I think this may be the last section. So a test is coming. Hope you're ready. If not, let me know so I can help you. Here we've got, it says Trey. Let's see, it says Trey is a buyer for a major department store. He just received a box of 1,000 shirts from a designer's new collection. Of these shirts, 560 are V-necks. Randomly choose a shirt from the box. Let the event A and the event B be as follows. The event A is the shirt Trey chooses is a V-neck. In other words, what this is saying is, what's the probability Trey gets a V-neck? And so you've got 560 V-necks out of the 1,000. Probably he reaches in there at random is going to be 560 over 1,000. It says write your answer as a decimal and do not round. So I type that in my calculator, or if you really had a good math teacher in elementary school, you would know that that probability of that decimal is going to come out to be 0.56. 56% chance of getting a V-neck. When we look at the probability of B, which is the shirt is not a V-neck, another way of writing that is the complement of A. That's the same, this says the same thing. If we know if A is getting a V-neck, this right here is not getting a V-neck, okay? And I know these two complements are gonna add up to 1, so I know that means that's gotta be 0.44. The other way I would figure that out is if there must have been 440 shirts that weren't V-necks out of the 1,000, and I'd type that in my calculator, I would have gotten that 0.44. All right, getting in some bigger numbers here, and we're writing probabilities as decimals instead of leaving them as fractions. Probabilities, just so you know, the probability of something has to be less than or equal to 1, greater than or equal to 0. If it's a probability of 1, that means it's a sure thing it's going to happen. If it's a probability of 0, it means it's not. We know for sure it's not going to happen. So if you ever try to type in, let's say you type in a problem, come up with a question, and you're working it, and you say the probability is 1.4, well, you know that can't be right because that probability is over 1. So just know probabilities have to be between 0 and 1. All right, last problem. All right, here we go. Homework 3-8. Here, we're just a number cube. We'll call it a die. You're rolling it 3 times. You're just concerned about getting odd or even. So you only have 2 outcomes, odd or even, on each roll. So remember, 2 outcomes on the first roll, 2 outcomes on the second roll, 2 outcomes on the third roll. There's 8 different possible outcomes when I combine all those things together. And you see them in a list here. E is for even, O is for odd. So the question for event A, the probability of event A is, what's the probability of getting an even number on the last roll? So what you're going to do is go through here and check whichever ones have an E coming up last. All of those even on the last roll. See, they all have an E being the last thing there. There are 4 of them, so you got a 4 out of 8 chance. No odd numbers on the last 2 rolls. No odd numbers on the last 2 rolls. So this is okay because there's not an odd number on the last 2. Is that the only one? Nope, right here. No odd number on the last 2. So there's only 2 out of the 8 where that happens. And then last one, alternating odd number and even number, with either coming first. So a situation like here, let's get a different color. I go odd, even, odd, or I could go even, odd, even. So I check that one, I check that one. Again, 2 out of 8 chances there. All right, let's try something a little bit more difficult.